Hello, everyone. Good morning. Welcome to another virtual hands-on session. Today, we're joined by Kevin Corbett from Festo, Canada, and he's going to be showing us a nice application. So, welcome again. My name is Sandro Quintero, and Alejandro Lopez is here as well. We're your usual hosts. And again, Kevin Corbett as our guest for today. Kevin, welcome, and thank you for taking the time to show us what you did here with this application.
Yeah.
Hey, thanks for having me, Sandro.
Yeah, just before we start, just want to tell everybody on this call that we're going to be having people maybe French speaking or Spanish speaking. So as we go through this, if there's any question or any comment in any of these languages, please feel free and we'll try to respond right away. If not, then at the end, you're going to see our contact information. Then we can get back to you if anything that is necessary. Okay.
Right. Yep.
Para todos los que están conectados, para todos los que están conectados en español, también los podemos atender desde nuestras cuentas de correo, o si de pronto tienen alguna pregunta, siéntanse a gustos y háganla y podemos hacerle la traducción si necesario. Pour tout le monde qui est en français ou qui parle français, vous êtes bienvenus à nous poser des questions et on va essayer de traduire tout ce qui est nécessaire. Okay, go ahead. Kevin?
Yeah, and just as a reminder, we're recording this session, so you're going to be able to watch it at a later point in case that you missed something or you have to drop off the session. Okay, just as a reminder, and Alejandro just mentioned, feel free to ask any questions. You can unmute yourself. You can type them on the chat. There's no stupid questions, really. We're all here to learn something, so feel free to ask any questions that you want. All right, so with that, our topic today is going to be linear measurement with simplified motion, and Kevin is going to be doing a quick explanation of what this is about. But before we jump into that, I also wanted to show this slide here. So in case that you have any questions, here are our email addresses. You can always send us an email, and we'll be replying. You can also reach out to us on LinkedIn. Okay, so with that, let me stop sharing, and actually I'm gonna make you, Kevin, a host, so now you can show.
We can show the Star Wars at the back.
Yeah.
Okay.
There you go. Okay, so Kevin, you told us that there was an application that you were working on where a customer wanted to detect different heights on different parts that were going through a production process, I guess.
Yep.
So tell us a little bit more about what were the challenges or what this was about. And I don't know if you have a picture that you can show or something.
Yeah, I do. So I'll show a picture of what it looks like now.
Okay.
Oh, I don't know if I'm actually sharing my screen yet. Let's do that. All right, so you guys can see my screen?
Yeah.
Perfect. So this is what the picture looks like now. Originally, when the customer called me for help, they had pneumatic actuators, just cylinders. So they're the extend and retract with position transmitters on them. And what the position transmitters do is on the pneumatic cylinder, there's a piston magnet, and the position transmitter follows the magnetic field, and it tells you what position the cylinder rod is at. So the idea was they would load a part, and the part would land in this area here.
Mm-hmm.
And then the pneumatic cylinders would extend, hit the part, and then they would do a read of the position transmitter. Now, position transmitters are not very good for measurement applications because they have what's called a linearity error. So when you're reading a position from a position transmitter, the position's not linear.
It's not like 0 to 100 millimeters and then you will get 0 to 10 volts perfectly linear. There's a certain deviation.
Straight line. So if you were to plot those values onto a graph, it wouldn't plot as a perfectly straight line. What you would get is you get little waves in it.
Right, right. And this is the expected behavior. In this case, you're talking about when you say position transmitter, you're talking about a sensor that's mounted on a pneumatic cylinder, and this sensor is detecting the piston, the magnet inside of the piston rod, or yeah, on the
Exactly.
piston, right?
Yeah, exactly.
Exactly.
Yeah, I
It's
think
using
that's
the
what it is.
piston magnet to determine what position the piston is at. So as the magnet moves away from the sensor or towards it, that magnetic field is now getting stronger, or is being detected at a higher value,
Mm-hmm.
and therefore the sensor will output a different signal, typically 4 to 20 milliamps or 0 to 10 volts. So you
Okay.
And
take
I guess there's all. Sorry, go ahead. Sorry, go ahead.
you take that measurement, so that's 0 to 10 volt signal, and you scale it to your stroke of the cylinder. So if you have a 100 millimeter stroke, you'll scale 0 to 10 volts to 0 to 100 millimeters. However,
There's
with
also
that,
something interesting on this thing is that you have to have a different kind of sensors for different strokes, right, Kevin? As you change the stroke or the length that you want to measure, you have to have a different physical sensor to attach to that magnet, right?
as long as, so depending on what your cylinder stroke is. So if you have a position transmitter that has a range of 0 to 50 millimeters,
Mm-hmm.
you could use a cylinders from a range of 10 to 50
Right,
millimeter stroke.
right,
And
but if it's a
changes.
super long, if it's a super long, then and you're out of the range of a standard sensor,
Right.
then
Yep, that's
you're not
right.
gonna
And
be
then
able
you
to
would need to
cut
get
it and.
a, yep, then you would
Mhm.
change to a larger
That's
sensor.
and
Yeah.
that's one of the constraints with position transmitters, right? That there are
Mhm.
only several lengths, and that's it.
Yep.
Like if you have a longer actuator, then you're screwed actually, because
Yep.
there's
Yeah.
not going to be a solution unless you use
Exactly.
two or something. But then it gets a little bit more complex.
Yeah.
So having said that, so that was kind of like the challenge, that
Mhm.
linearity error, right? That was the main
Right.
challenge.
Right.
So
Mhm.
what did you guys do in this case to overcome this challenge?
Well, last year Festo released the Simplified Motion series, which is what we're looking at here. And basically, what this is it's a compact servo system that acts like a pneumatic cylinder. So control is very simple. You just have one signal to extend and one signal to retract, which is similar to how you would control a pneumatic cylinder. You have
Are,
one or two
are
coils, and that'll
they
control.
are they like a physical signals, like a 24 volts in a pin or something?
You have two options. You can do IO link, or you can do digital signals.
Okay. Okay.
In this case, we're using IO link.
Okay.
Now, for position measurement, they have a built-in encoder. So that encoder counts the pulses of the motor rotation. So you can actually track in a very linear fashion what position the cylinder is at. So now that linearity error, it's no longer an issue. Now we get a nice, constant
Signal,
measurement
Line.
right? Feedback
signal.
signal.
The
So
nice
I
thing is
have
also
here,
you don't have to have a different length on the sensor. I think that's one of the challenge that I had before.
right?
Yeah.
I
Oh,
have
and you
here
don't
one
need
of
a
those
sensor.
actuators that you're talking about, right? This is the one of the SMS. There you're using maybe a different shape or something.
Yep.
But so this is what you're talking about, the SMS, right? And
Yep.
it's basically a motor that's mounted on an axis. You can see, well, maybe it's too long to fit in the camera, but it's just a motor mounted on there, and then you have this carriage that moves through the axis,
Yeah.
and
Yep.
and you're controlling this in your case how?
IO-Link.
IO link, okay.
Yeah.
But you can also control it via digital IO, right?
Yeah, exactly. So you could just hook your PLC outputs up, two PLC outputs up to the two digital inputs, and that's all you need, and then
Okay.
you're
Okay.
ready to go.
Okay. So is this like a specific environment, or where is this mounted?
So this is on a fixture
What
for an
kind of industry
automotive.
is? Oh,
This is
automotive industry.
an automotive manufacturer,
Okay.
and what they're doing is they have square bars, like steel bars, and they're cut, but they need to be cut to a specific spec. And if they're outside of that spec and they get shipped to their customer, then they get in big trouble. There's fines and all sorts of issues happen. So
Mm-hmm.
this is a measurement station. So they've processed the parts, they've cut them to size, Now a robot grabs them in batches and then it places them down on top of this fixture.
Okay.
Okay.
That's nice.
So, okay. So tell us about how this works. I see that you're showing here the video. I mean, there's a feedback there on the video.
Yep.
So how does it work? Just as an example of one run, I guess.
Sure. Do you want me to do a quick
Yeah,
run? Or?
Just a simulation or something.
yeah, I
Yeah.
suggest that you stop sharing your computer screen and then just do a spotlight on the video so we see it as the main thing.
Yeah, that's a good idea. Let me do that. So stop sharing.
Are they
Yeah.
different sizes? I never worked with this one before.
Yes, there's different sizes.
Okay.
Phone,
Sounds interesting.
spotlight video.
There we go.
Cool.
Yeah.
So
now we can see it.
did it do that for everybody?
Yeah.
Yes.
Yeah, I
Awesome.
can see it here. Big one.
Cool.
If anybody has any question or any concern, just please let us know as we walk through this exercise. Go ahead, Kevin.
Okay, so what I have here is this is Festo's ELGS, Simplified Motion Series. It works just like the one that Sandro just showed us. So this carriage here slides back and forth. What I'm gonna do is I have my 3 parts here. And what I'll do is I'll measure them. So I'm just going to place the part in front of the carriage, and the carriage is going to go. It's going to extend, and then it's going to hit the part. And then that's going to trigger a done bit, which is going to tell the PLC to pull the...
And Kevin, before you do that, I just want to clarify something. So you are using this actuator in a very specific way, which is to measure a certain dimension, right?
Yep.
But usually, I mean, you can use this for an application for positioning only. Like imagine that you're doing just extend and retract. Maybe you're opening a chute or something on a conveyor. Let's say imagine a conveyor, right? So you have a conveyor, and then depending if you want to
reconfiguring the machine, you mean?
Yes, change maybe a setting or something on the machine. You can just extend, and then you have a different configuration. Retract, and you have a different configuration. So I guess my point here is you can use it in different ways. Right now, you're using it in a way for measurement, but it can also be for positioning, right? So
absolutely.
Yeah.
I think positioning is what we mostly think about when we look at these kinds of actuators. This is a nice airless alternative to pneumatics. However, I think in this application, we're using it kind of in a creative way to solve a unique problem that doesn't work.
Reconfiguration of a machine will be a very nice, especially because if you run an IO-Link, I can see, well, IO-Link is point to point, so you don't compare this with an EtherCAT or Ethernet IP or Profinet motor adjustability, but you can go point to point from a IO-Link master maybe on the field and then run all these directly.
And Alejandro, I know that you have not used this before, but there's a cool thing about this too. If you think about it, think about when you use a pneumatic actuator. You have a pneumatic cylinder, and this pneumatic cylinder, the only signals that you need from the PLC is just extend and retract. That's it. Just 2 signals, 2 bits. And then in turn, usually on the pneumatic actuator, you have sensors mounted on the extend and retract, right? And you get 2 signals back. So the nice thing about this is that you can just drop in this and use those same signals that you were using before for the pneumatic actuator and do the movement, the same movement. So that's one of the...
sounds simple.
Exactly, and you touched on the key point here, simple. That's why this is called Simplified Motion Series, right? But anyways, that's the simplest way of using this actuator. Now, Kevin, sorry for the interruption. Go ahead and show us how
run
you
it.
do it with force.
Yeah, for sure. So let me, here, I'll put this one in. So let me just go here.
Yeah, adjust the current on the motor and everything else via IO-Link also, I guess.
Yeah, so this actually has two operating modes. We have a
run it as you talk.
Yeah, sure. So this is called a press mode. So let me just retract, and I'll do that one more time.
Yeah, it goes fast, and then
So watch, this is
try to
advancing.
find a
Now
window.
now it switches into press mode.
Mm-hmm.
And when it switches to a press mode, it's no longer looking for a target position. Now it's actually looking for a force limit.
Mm-hmm.
And what we can do is we can set the force limit in increments of 10% increments of the total force. So 10, 20, 30, 40, 50% of the total force. So
That's nice.
yeah, so here it's searching for the part, and once it hits the part and reaches, in this case, 50% of the total force, it says, all right, my motion is now complete. And then from there, we do a read of the current position, and we know where the part was when we hit it.
Yeah.
Kevin, I think this is a really nice feature, being able to approach quickly and then slow down. Typically, when you want to have a repeatable measurement, what's key is to have a repeatable force. Typically, low force is preferred to be able to deform the part less. But in pneumatics, if you're adjusting your pressure regulator to be low force, you're also going to influence your speed. So now that may become a challenge with cycle time. So it's nice to know that you could speed up in the approach and then go to a low force, so you can have an accurate, more repeatable measurement. So that's
Yeah,
very nice.
actually, that's a good point, because you can run this for a capping situation where you can go really fast, approach to a cap that was previously pre-located, and then press with a particular force and then measure. So that's a nice feature, and then you don't affect the cycle time necessarily.
Right.
Exactly, that will be a nice feature. Are you able to also pull force values when you're doing the contact? So you could, let's say, data collect not only the position or the thickness, but also a force out of it?
Yeah, you can. And that's for very simple pressing applications, it works great. So say you're inserting a seal into a part, and you want to make sure you see a certain amount of resistance as you're pressing that seal in, and you also want to make sure it goes to the right position. So here you can say, all right, I reached my target force, and I also reached my target position. So that'll let you know that you have a good part, because there's lots of presses available on the market, but some of them can be complex and expensive, where you don't need all of the features that come with those, where this is a great, simple solution, easy to set up.
Now that you mentioned the monitoring, what's the capabilities of this system to do, how when you have a servo press, you can do window control for when you start to touch the part, or even like envelope monitoring through the press cycle. What are some of the features in this simplified motion series? Is there a min-max force? Can you do windows, or how do you visualize any sort of data?
So no, you can't set any of those up in the actuator itself. All we can do is monitor we can see the current position and what the force reached was. We can see those two values.
Okay. But you could technically monitor those on the PLC or something, that you reach.
Yeah, of course. You can set a window
like
limit in your PLC and do a real simple comparison.
Can you show me the screen, like the IO link, maybe? Or did you finish with this demo? Or maybe I can let you go and then maybe show us the configuration portion, or where you can.
I can show you that. This part's pretty straightforward. The actual actuation. I have a sample here on my screen of a configuration using a Festo code assist PLC. So you can see how all the
if you think about how what you mentioned, Sandro, if you replace a standard cylinder with a hose or a tubing and 2 cable sensor, then you're pretty much replacing with the same kind of thing. So you can bring 1 cable for power, 1 more cable that you can split in 2 sensors, and then you kind of replace a pneumatic system with this fairly quickly.
Exactly. Yeah, and the other thing, we already talked about the simplified way of the actual hardware of the mechanical side, but I also want Kevin to show the what kind of commands you need. So for example, and I guess you can show them here in the control parameters, right?
So I'll start with the process data. So this is the control parameters for extending, retracting,
Sorry, Kevin. Let me interrupt you for a second.
Yep.
Can you explain the hardware, because we're familiar with this, but maybe people on the call, maybe they're not fully familiar. So here we have CPX IO-Link master with 4 channels. So in theory, you can plug 4 motors of this directly to this,
Yep.
and then you have like a PLC, right? Like a Festo PLC.
Yeah, correct. So what I have here, actually, you can see on the screen,
There you
is
go.
the Festo CPXE.
Mhm.
On my network, I also have an EtherCAT slave, but we're not using this here. It's just
So
part of my
the one
network.
on the left is the PLC, that's the controller, and the one on the right, that's where you have a card with IO-Link, with an IO-Link master.
It could be in there, but in my case, it's actually on the PLC itself. But you could have it on either or.
But
it would
you can
work
also,
on both.
yeah, or you can also have an external, like a remote on any other PLC. I don't know, Beckhoff, Alan Bradley, Siemens with an IO-Link master, maybe remotely connected where the machine is, and then you can run everything from that particular IO-Link master.
Yep.
Everything on M12 connections.
Correct.
Okay, that's nice.
All right. So yeah, go to the IO-Link card again, that screen that you were showing us.
Sure.
The one thing that I wanted to mention here is that this part here is something that you see in any IO-Link master, right?
That's true.
This is truly nice, because it doesn't mean that, oh, I have to be familiar with the Festo software. No, this is a standard IO-Link. So you will see process input, process output data. You will see the parameters. All of this happens on all of the other brands for IO-Link Master. So it's pretty cool.
Mm-hmm.
Okay, so tell us about the mapping that you have here. So I see that it's pretty easy because you have some bits, only bits, which is either false or true, and that's it.
Yep. And there's really not that many of them. There's not a lot to keep track of here.
Yeah.
So for our control, we have 3 bits. So we have a move in and a move out. These are like your solenoid coils on a pneumatic valve. So they control your extend and your retract. And then if any faults or anything happens, we have a quit error.
Or reset, right?
Simple.
Or a reset, reset.
That's pretty simple.
Yep. So that's it. So in your PLC logic for actually controlling the actuator, that's all you need. And then for the data coming back, we have a state in, state out. Those are like your read switches. So they're going to tell you when you're extended, when you're retracted, or when you've reached your target force. So in press mode, state out becomes like a force sensor almost, where it's going to tell you, I have reached my force limit.
I'm at the forced target, right?
Target force.
Yeah.
Yep. And then we have a state move. So that tells us if
it's moving.
Yep. When you're in motion.
Mm-hmm.
And state device. So that just means if it's true, it's good. If it's not, there's
something wrong with it.
Something wrong, yeah. Mm-hmm. Actually, an interesting thing to bring up about this is the so your power stage power and the electronics power. So the electronics is actually what allows it to communicate. So it's online, and we can monitor the status of these bits. And then the power stage is what actually is required to make it move. They're separate. They're on separate connectors, which you can.
So you can actually tie that into a safety relay and cut that line, right?
Yeah, exactly. So now if you're doing like a part load unload station and you want to disable the power stage, so that way an operator can
retract
load a part on, you can disable the power to this connector right here, which is going to be your power stage, and now it's disabled.
That's nice.
Oops.
Through my phone.
Oh
yeah. So that's actually pretty cool,
nice.
Because you can drop the power then. So if I don't know, an emergency stop is pressed, you drop the power to the motor and it's going to stop moving, but you don't lose control over it. So
you're still monitoring it.
You're still monitoring it. It'll tell you there's something going on. I lost power. You're probably going to see that bit that you have here, state device, is probably going to go to false instead of true, and then you gotta see what's going on.
Kevin, do you still monitor the actual position when the e-stop, or in this condition, the power is cut, right?
Exactly. So when you cut the power stage power, the only thing you lose is actually the ability to make it move. It goes into like a floating state. So right now, because it's enabled, I can't move it. It's maintaining its position. It's going to stay there. If I disable the power from the power stage, I can now, it'll float. You can move it around, right? Which is great for setup as well.
Okay, that's good. Okay, and what about the IO link parameters? Can you walk us through?
Yeah, of course.
Fairly
So now,
quickly.
so this
We
is
don't have a lot of time. We have 5 minutes left.
Okay, so I'll
Questions.
be quick with this part. So this is the process data. This is the parameters. In the parameters, we can set our limits. Like for example, our force. We can come in here and we can change, right? And as I mentioned earlier, the force limits are set in increments of 10%. We can change our start press position. So when I actuated the actuator and it goes from fast motion and then drops its speed down into force mode, we can change where that happens, right?
Pretty cool.
Okay.
So that way you have control of where that quick advance ends and then force begins.
I see that first parameter that you have there, local user interface lock. That
was my question too.
Yeah.
Oh, yeah.
That's nice. You can lock it for people, I guess, interacting directly with the motor.
That's a super common question from users, right? Because Kevin, you can probably show on your camera there that there's blue buttons on the motor. Actually, there's like a keypad that you can use for commissioning or moving, right? So you can extend it or retract it manually if you want it. So those are the LEDs. But if you flip it, you can see the buttons on the side there. So this bit that Kevin is showing on his computer, local user interface lock, if you make it true, then those buttons will not work. This is a very common request because you don't want operators to be tweaking those motors on the field, right? So pretty cool. Yeah.
Yeah, you can lock them out, and also though these buttons are an important point to touch on. You can use those buttons for setting all of these parameters. So if you don't want to come into the PLC and change these parameters through here, if you're more comfortable just doing the setup with the buttons, you can do it all from here. In my case, in the application that I worked on, we didn't have access to the buttons, so it was actually a key for us to make those changes over IO Link.
You know what I like about all this is kind of field ready, feel like to mount it on the field. So you can have, as I said earlier, you can have a master on IO Link M12 connectorized, and then plug all these, and you only come back to the cabinet with one single cable plus the power. That's what I like about from what I can see.
Your communication setup is very simple. You don't have to go in and set IP addresses, node numbers, any of that. It's just you tell the IO Link master, I'm talking to an ELGS on port 1, and plug in the cable, and it takes care of the rest.
So we're almost running out of time. We have like 2 minutes left. I would like to remind people that you can ask questions at this point if you have something for us or for Kevin. And Kevin, I would like you to do some conclusions, if you like, about what we saw today.
Yeah, sure. So the SMS is a great alternative to pneumatics, especially in applications where you want to be able to accurately read current positions, run force moves like force motion. Setup is simple. We can do it through the interface on the actuator itself or through IO Link directly. These parameters are stored in your PLC over IO Link. So if you ever need to replace the actuator, you only do it once. You just unplug the old actuator and then you can plug in the new one.
So something that you didn't show though, and we just have like 1 minute or a couple of minutes, the visualization. So can you run it again, showing the visualization so you can show us the actual positions that you were talking about?
Sure. So let me put a part in, and
so with just 2 signals, there, that's better. Yeah. So just with 2 signals, now you commanded it to move in, and then you're gonna command it to move out, and then it changes the speed and it touches the part. And as soon as it touches the part, we get this light, this yellow light, also on the right. Down below that one. That one is saying I reached the force, right? And then once it reaches the force, on the bottom, you can see that scale that is telling us this is the distance that I detected. So now put a new part. That was, I noticed that that was almost 120. So
And you get an actual reading value out of it, not just on the scale. Is that possible?
Yeah, that scale is using the value. I'm just using this visualization to actually display what it is, but there is a real value coming back.
Yeah, I was interested on the actual, significant digits when you're kind of repeating that measurement action.
Yep, two decimal places.
Yeah, you get 2 decimal places out of it. Okay.
Yep.
So that one was almost what, like 155, I believe. And then this one should be less, I think. Yeah, 135. Well, 133 or something like that.
Can you, hey Kevin,
Yeah.
can you show us the value, like the real value coming out from the device? Yeah, as somebody mentioned about the
133.
Ideally, if you can cycle back and forth on the same part, and then we'll just see that value come back.
Ah, okay. So he wants to see if you can run it again. Let's see what's the value that we get.
Exactly, for measurement, repeatability, it's key. Exactly, just to get a feel for it.
133.37, so 34.37.
Now, keeping in mind you don't have any, sort of metal machine parts with like.
Put the white one. Put the white
surfaces,
part.
But
yeah,
Kevin, put the white part. That one is more square from what I can see.
Yeah, because he could have some variations when the part is twisting or something, right?
Exactly. When you contact it may sit differently. Yeah. Exactly.
Now it's
So I guess this first run shouldn't count because now the part is seated. Run it again. Run it 2 more times, and then these next two times should be the ones.
Yeah, but normally you get only one chance.
No. I mean because he's just manually mounting it.
119.09.
119.09.
Again?
Yep, 119.09.
Oh.
Yeah, just double click on it.
There it is.
119.09.
There it is.
It's not bad.
Yeah, it's actually pretty
just to try repeatability and things like that. That would sounds simpler. Yeah.
119.09.
Exactly.
Pretty cool.
Repeatability is key for the measurement. Trustworthiness, call it that. But yeah, very nice.
Okay, Sandro, we're almost getting to the last.
Yeah, no, actually we're over time. So I think we covered a nice conclusion. Kevin was able to show the visualization, how it works. And you probably noticed that on the visualization, it was just 2 signals, extend, retract, two lights showing I'm extended, I'm retracted. And then Kevin added another bar there to show the actual position. So pretty easy. Of course, I mean, remember that this is a simplified solution, of course. If you have something more complex where you wanted to do, I don't know, more complex movements, I don't know, a cam application or something, we at Festo, we have some additional controllers, right? Higher end controllers that can do way more things. This is only for simple applications, of course. So with that, I think we can finish. If there are no more questions, I think we're just going to hang around for a couple more minutes in case that anyone has questions or want to type them on the chat. We're going to be here. Kevin, again, thank you very much for your time.
Thanks, Kevin. That was really nice.
And Alejandro,
again,
thank you for joining us.
Yeah, that was really nice.
Great.
Very
Thanks
nice,
for the presentation, guys.
Very nice. I think we're gonna try in a couple weeks. We have couple more guests, so we're gonna have to find out who is gonna be next. And we'll invite you guys over our social media channels, mainly LinkedIn. Thanks for participating on this. We hope you can learn a little bit from this. And thanks, Kevin, again for joining us. How many participants do we have?
So today we had people from California, from the United Kingdom. We had people from Tennessee, from Canada. So, and myself from Chicago. So pretty good turnout. The next session, I think, as Alejandro was saying, we're probably going to have a guest. I'm thinking maybe the Netherlands. We have to ask one of those guys and see.
We're trying to convince them.
Yeah, try to convince them. I'm pretty sure they're gonna be excited about showing something here. But yeah, keep staying tuned, and we'll be talking to you in a couple more weeks. Remember that this happens every couple of weeks on Thursday mornings. All right.
All right, guys. Thanks for joining us. Have a good day.
Yeah. Thank you all. Bye bye.
Thanks.
Bye-bye.
Have a good one.
Bye.
Thanks,
See you
Kevin.
guys.
Bye.